So this number, 340 watts per square meter, was the one we used before our little chocolate experiment. And we have to understand how this 340 watt actually come about. The sun is a very hot body and therefore emits its energy as visible light. So the peak radiation is the visible wavelength. The Earth is a lot cooler, on average seen from space about -18, -20 degrees Celsius, and therefore emits its energy in thermal infrared. Here you see the wavelength of the electromagnetic energy, and you see here the sun peaking at this wavelength, that's with a visible light, and here you have thermal infrared. So you have to kind of keep that into consideration, and at the normal or the average distance of the Earth, it's about 150 million kilometers from the sun. The average intensity of the energy received on top of the atmosphere, which is directly facing the sun, is this amount, 1,360 watts per square meter. Wait a second, you would say. Well, we just talked about 340 watts per square meter, and you're right, I used that number. This number is the total solar irradiance, formerly called the solar constant, and now we need to think about how do we get from 1,360 watts per square meter to the 340 watts. Well, it has to do with the angle of the incoming energy. And here, if we have the sun on this side, the incoming sunlight is hitting the Earth's surface, and there is only one point in time which is directly facing the sun. So this square meter here, where the exact amount of energy is received, is the square meter with the 1,360 watts. If you then remember the Earth revolves once per day, there's also other sides here, and that's the geometric constraints basically, that the same amount of light is distributed over a larger area. So the same amount of energy is given to not just 1 square meter, but more than 1 square meter. And therefore, we can reduce our large number here, 1,360 watts, to that average, global average energy received of 340 watts per square meter. So the entire planet, averaged over the entire planet, the amount of sunlight arriving at the top of Earth's atmosphere is just about 1/4 of this solar irradiance, and it is this 340 watts. So we made it from the solar irradiance to 340 watts per square meter. So that's what we have to deal with on average on the top of the atmosphere. Now, if you want to stay in somewhat balanced temperature, whatever energy you get in, you need to give away, otherwise you will heat up. And so we have to state that the energy which the Earth receives from sunlight must be balanced by an equal amount of energy which is radiated back to space. And this energy, we just talked about the different wavelengths, escapes in the form of thermal infrared. So that's if you stand in front of a fire or stand in front of a heat lamp. That's kind of the type of energy which the Earth is giving off. And it's giving it off in all directions into space. The net flow, so calculating how much is coming in and how much is going out of the Earth system, is called the Earth's energy budget. If we think about the Earth's energy budget and we put in this term radiative equilibrium, it is logical that if you have as much energy coming in as you are giving off, so if those two numbers are equal, Earth must be in radiative equilibrium. And therefore the global temperature is relatively stable. We also know there are these internal feedback loops and lots of other more difficult things, but in general, to make it easy, if you have the same amount of energy coming in, equaling the amount of energy being given off by the Earth, then the temperatures should stay stable. And anything, and that's the logical consequence, if there's more coming in, you need to be giving off more, otherwise you heat up, or vice versa. If not as much energy is coming in, you will cool. And those are basically very simple responses of the global temperature, which have to rise and fall in response to the direct amount of energy received from the sun. And that's basically this left side of the equation, whatever is coming in must be equaled by what is going out, and the resulting temperature you see here on the right side. Now let's make it a little bit more graphical. On the left side here, we have the Earth's energy budget, the incoming part, so the yellow arrows. And on the right side, we have the outgoing part, so the red part of this graph. The incoming solar radiation here is exactly the amount we had before, the 340 watts per square meter. And we can also see that there is some amount of this is reflected directly back to space on top of the atmosphere, for example, by clouds. Some of it is reflected at the Earth's surface. But all in all, taken together from 340 watts per square meter, about 1/3 is reflected directly back to space. Parts of it directly on top of the atmosphere and parts from the Earth's surface. From this incoming solar radiation, 23% is absorbed in the atmosphere and 48% is absorbed at the surface. And so now you would say, well, I mean, this is just one number, the 340 watts per square meters, but how does it actually work over the different seasons? And you see, this is a graph of the Earth's orbit around the Sun, a very, very simplified graph of the Earth's orbit around the Sun. But we see here that it's actually not a perfect circle, it's an ellipse going around the Sun. And you also see that this is calculated for the northern hemisphere. You see that the northern hemisphere is tilted away from the Sun when we are relatively close to the Sun, and it's tilted towards the Sun in the so-called aphelion when we are a little bit away from the Sun. And so you have this way here, you have the equinoxes, basically when the day length is equal over the whole globe, and then you have the solstices, the winter solstice and the summer solstice. And of course, all of these variations do vary the amount of energy received. And therefore, there is another point we have to think about. Here we have the months. So January, February, March, April, etc. And here we have the latitude. This is the equator. And these are northern latitudes. This is southern latitudes. And the graph shows the incoming solar radiation in watts per square meter. That's exactly the number we have been working with. So the average is somewhere here, 340 watts per square meter. But as you can see, the average is composed of many different patterns. And these patterns are due to the different seasons and also by how the Sun is tilted away. And now my question to you would be, well, if we put those two together, to really understand the input of the energy from the Sun to the Earth, where is the highest amount of radiation received per day and why? This is the graph mapping the incoming solar radiation. Here is the other information you need to answer that question.